This video is designed to help amateur astronomers understand what is happening inside their mount when it is tracking an object through the sky. The equipment used is described in detail on our website at www.helver.co.uk. The object in the primary and in the guide view, that's top left and top right respectively, is the same star, SAO 110665. This star is within half a degree of the celestial equator. During my recording time it traversed approximately 15 degrees of azimuth between south-southwest and southwest and dropped 5 degrees of altitude. It is possible, the process is documented on our website, to calculate the field of view of the camera telescope. It is possible to calculate the field of view of a camera and telescope combination using the detail of the focal length of the scope and the physical dimensions of the imaging sensor. The process is documented on our website. However, here we will use our knowledge of simple celestial mechanics to calculate the field of view of the C8 OTA and camera combination based on timings from the video. The guide scope focal length is approximately 1/4 of that of the focal length of the C8. One of the primary objectives of this video is to demonstrate that the declination or deck gear does not move during tracking, except for when the operator is slowing the object of interest into position, and only during guiding if there is a correction pulse sent from your guiding solution. This slew demonstrates that the x-axis of both cameras are oriented in parallel to the right ascension axis of the mount. We can add the 8 seconds to drift in and out of our field of view together, giving a total transit time of 16 seconds for the whole field of view. Knowing that the star of choice is on the celestial equator, or close enough to make no difference, we can calculate the field of view from the approximation that the Earth rotates once in one day, which is 24 hours. So giving 360 degrees in 24 hours, or 15 degrees in 1 hour, or 1/4 of a degree in 1 minute, or 1/240th of a degree in 1 second, 16 degrees to transit the field of view give 16/240ths of a degree, or 1/15th of a degree, which is 4 arc minutes. Here I have taken 18 minutes of real-time recording and played it back at 20 times speed, adding an echo to show the apparent movement of the star relative to the camera's field of view. Zooming in on the curve plotted out by our star, we can estimate the periodic error of the right ascension drive by simply measuring the peak-to-peak data. In this case, we can see that the peak-to-peak of the curve covers approximately 1/4 of the field of view, and we know that the field of view is 4 arc minutes, so we can estimate the periodic error, or PE, at 1 arc minute peak to peak. I've not calculated the alignment error. Software on a modern go-to mount would do that for you once you have completed your alignment procedure. But you can see from the presentation that a star in the south is causing drift to the north. So the geometry of our alignment tells us that as a minimum the polar axis is too far to the west. You will also note that other than for recentering the star manually, thus far there has been no movement in the declination axis. Again at 20 times speed, we see that adding guiding does not produce a perfectly circular star. This is impossible due to factors such as seeing, collimation, and the fact that guiding corrections are only added once a star has moved out of position to push it back to its original place in the field of view. However, the improvement is significant, as can be seen here. Taking the apparent error from the order of 1 arc minute in 8 minutes of exposure to under half an arc minute for the same film or exposure duration. Assuming that the auto-guider performs without error over time, which is by no means a given, then auto-guiding ensures that the target will remain within a relatively well-defined area, as opposed to the constant oscillation and continual drift away from the start position, which is experienced through tracking alone. Such is the difference between an open and a closed loop control solution. I hope that you have found this video to be useful and informative. If you've got any questions or comments, please don't hesitate to either contact me via the website or by placing a comment on the video. I thank you for your time and look forward to hearing from you in the future.